For pre-calculus, we are at the end of Unit 9, and we are going to be talking about speed and direction. Okay, so when we're thinking about speed and direction, let's consider an airplane. So it has a specific course that it sets on, all right? So it's got a course with a specific direction. We're going to call that vector 1. That's going to be our airspeed. Bleh. And then the wind, of course, is going to push it in another direction. We're going to let that be vector 2. So what happens to the airplane is that as it sets its course, the wind is going to push it off course, and that is going to result in a new vector for the airplane. So the result of these two is actually going to be the ground speed. So of course, an airplane, when it's in the air, it adjusts to the wind, but how fast it is going is determined by our ground speed, which it would be the result of being pushed off course a little bit by the wind. But an airplane, of course, is going to adjust to that, but it's still going to affect how far it goes in a certain amount of time. Okay, so let's draw a picture of this so that we can get a little bit of an understanding of what we're talking about here. So let's say we have vector 1. This is the airplane's course, all right? So this is what the airplane sets off to do. Well, let's say the wind comes up from the southwest. All right, so let's say the wind does this and it's going to push. Okay, so this is the wind. So that's going to represent vector 2. And what results, okay, the resultant vector is that the airplane actually ends up right here. So this is our resultant vector. All right, so the important thing you need to know about this is that we have a relationship between these three vectors. There's a mathematical relationship, and that relationship is that the resultant vector is equal to the original course plus the force that acts upon the original course. So this, of course, is going to be your resultant. The V you can think of as your original course set by the airplane in this particular situation. And then the W is going to represent the force that acts upon the original course to give us a resultant vector. So that is what we're looking at here. Now, the nice thing about having a mathematical relationship between these three vectors, we can use this equation to solve for R, V, or W, either one. So we can use it to solve for the force, we can use it to solve for the original course, or the resultant. If we're solving for the resultant, obviously we'll just add these two together. If we're solving for the original course, we will just subtract the force from both sides. And if we want to find the force, we will just subtract the original course from the resultant. So we can use this equation for all these problems. All right, so let's jump in here and look at example 1. Now, on example 1, to kind of guide you through this process, I have it sectioned up into the different things, different steps we're going to have to go through. So this example is going to take us a few minutes. So we have an airplane traveling at a speed of 500 miles per hour with a bearing of 330. The plane reaches a certain point where it encounters a wind with a velocity of 70 miles per hour in the direction north, 45 degrees east. What is the resultant speed and direction of the airplane? So the resultant speed and direction, we have to find speed and the direction of the airplane. So essentially what we're doing is, in our equation right up here, we are looking for R. So we're going to set this up so that we find the original course. We use the original course and the wind. All right, so the very first thing we're going to have to do for our solution, the vector V is going to represent the airplane's original path, and we are going to find this velocity vector. So remember how we do that. We take the speed, so the airplane is going at 500 miles per hour, and we're going to multiply that by the cosine of the direction angle. So we have to find the direction angle. We know its bearing is 330, and remember, bearing always starts north and goes clockwise. So we're going to go all the way here. So that's 330 degrees. That's the bearing. Now we want to find the direction angle. Remember, the direction angle always starts positive x and goes counterclockwise to the vector. So if the bearing is 330, that means that my direction angle is quadrant 1, 90 degrees, plus this right here, which would be another 30 degrees. So my direction angle is 120. And then, of course, I have to find my vertical component, which would be my y component. And then, of course, I just use my calculator to find that. And I get, for my two components for the airplane's original course, that right there. Now we're going to do the same exact thing for the wind. So it's the force. Its speed is 70. And we have to find its direction angle based on its bearing. So its bearing is north 45 degrees east. So its direction angle, of course, is going to start here and go to here. So that would be 45 degrees. So 70 times sine of 45 degrees. Of course, going to plug all of this right into my calculator. And I get a component form that looks like that. Okay, so the resultant vector is going to occur when I add those two together. So my resultant vector is v plus w. So that means I've got negative 250 for 33 plus 49.5, 49.5. So remember, we're going to keep our horizontal components together. So negative 250 and 49.5. When I add those together, I get negative 200.5. And when I add these together, I get 482.5. So there's my resultant vector. Now, the magnitude of r, which is the resultant speed. So remember, always go back to this. I'm looking for the resultant speed and the direction of the airplane. So the magnitude would be my resultant speed. So I'm going to take this. This is my resultant vector right here. So I'm going to use it to find D and E. All right, so the magnitude of r, remember we use the distance formula. So we're just going to take this value, square it, add it to this value squared, and that gives me 522.5 miles per hour. So this is the speed that results from the original course with the wind acting upon it. So we are halfway done with our answer. All right, now we want the true direction of the plane. So in other words, we've set a course, but the wind pushes us. We want to know where we get pushed. So again, we are using this right here. So I am going to draw a picture. Well, I've got negative direction, so negative, I'm going to use a different color here so you can see this better. So negative 200.5, remember the negative's just for direction, and then a positive 482.5. So that's going to be right up here. So 482.5, and then of course my right triangle with theta. All right, so if I want the direction of the plane, I've got to know some angle values here. I've got to know this angle measure, and I've got to know this angle measure so that I can write my direction correctly according to a bearing. All right, so I'm going to use tangent, theta, and it's opposite over adjacent. So theta, remember in your calculator, you type in tangent inverse of all of that. And then for theta, I get approximately 67.4 degrees. We are not finished. All right, so if this angle is 67.4, then this angle right here is 90 minus that, so that's going to be 22.6 degrees. Okay, so this is north and this is west. So the bearing or direction of the plane, you can think of it as north right here, 22.6 degrees in the west direction, or you can get a true bearing. Remember that a true bearing starts north and goes all the way around to the vector. So that would be 90, 180, 270 plus 67.4, which would give me 337.4 degrees as a true bearing. Either one of these works. You don't have to do both of them. So notice that in this problem, we have to do a lot of stuff. We have to find the vector velocity for our original vector and our force vector, and then we have to use the relationship, the mathematical relationship of these three vectors to find the resultant one. Then we use that to find the speed and the direction. Easy peasy lemon squeezy.